So my name is Zhang. Today I will present our work, learning production optimize the congestion control selection for Alibaba Cloud. This is a joint work with Alibaba Cloud, Sanyu University, and also Nanjing University. So today's CDN serving as a backbone of the internet handles over 70% of global internet traffic. Among all the services hosted on CDN, short video services has become a major workload for the CDN network. From a network standpoint of view, short video services can be mainly characterized by its low volume traffic and QE preference of rebuffer rate. To stand out from competitors, CDN providers has always strived to enhance the user QE as well as reduce the bandwidth cost, which constitutes a major operational cost of their expense. So to summarize, the goal of CDN provider is just to improve the user QE and reduce the bandwidth cost to stay competitive in the market. So what are the options available for CDN providers to optimize QE and reduce bandwidth? So the first category of approach targets application layer strategies. This includes using ABR to adapt it to network conditions and prefetching short videos to the client side, or upgrade to HTTP 2 or 3 to improve network performance. However, all of these approaches need to be implemented at the client side so that they are out of control for CDN providers. And the second set of approaches target transport layer strategies. Existing methods concentrate on modifying one type of CC or congestion control. So this could include either fine-tuning the parameters of congestion control or inventing a new CC by using some machine learning techniques. So they all have their own constraints. When tuning the parameters of CC, we found that they cannot fix the inherent design limitations of CC. This is evidenced by our experience in tuning cubic for 4G network, where much more bandwidth must be needed to achieve a similar QoE. And by designing a new CC, often they lack sufficient production testing. Therefore, they cannot provide worst-case performance guarantee. So we conclude that a single CC might not be sufficient for optimizing a CDN network. And our measurement study further reveals that no single CC can be optimal globally. So we have conducted an A/B test for 2 weeks comparing performance of cubic and BBR across all regions of China. So in this plot, you can see that the blue color means cubic is better, and the red color means cubic is better, and the blue color means cubic is better. Sorry. So the red color means cubic is better, and the blue color means BBR is better. So as you can see, the relative advantages of each CC can vary significantly across all regions of China. In addition, when we zoom in on a single CDN node and comparing the cubic vs BBR over time, we can see that also the relative advantages can fluctuate over time. So from that, we conclude that we need a dynamic and adaptive approach for congestion control selection, where machine learning could be a promising solution. So we propose AliCCS, the first machine learning-based congestion control selection framework for short video delivery in production CDN. We overcome the inherent limitations of each CC by dynamically selecting the optimal CC for certain scenarios. We also provide worst-case performance guarantee, as we are selecting from the well-established congestion controls, which are known to provide performance guarantee. From our experience, we have identified 3 key challenges in applying machine learning for congestion control selection in production CDN. So the first one is scalability and generalizations. So due to the scale of CDN network, it becomes impractical to train one model per node. Therefore, we need to train a unified model and deploy them across all the CDN nodes. And secondly, the interpretability of the model. During the incremental deployment, troubleshooting and iterating over the model design requires a clear understanding of the model behaviors. And thirdly, we need to reduce the inference overhead. Due to the complexity of deep learning models, we need to minimize the impact of a model inference delay as much as possible. So we will start. I will start with the first challenge, the model scalability and generalization. So I want to first share with you some of our key observations on the factors that influence CC selections and how that drives our designs. So basically, we have compared cubic and BBR based on the network types. So basically, in the 4G network, we can see that BBR consistently outperforms cubic over time with a lower rebuffer rate. And on the Wi-Fi side, it's exactly the opposite. Cubic outperforms BBR with a lower rebuffering rate. So we can see that there's somehow a strong correlation between network types and congestion control selections for short video services. To further confirm this insight, we also run a feature analysis on the network metrics. So basically, in this plot, we show the information gain of all the network metrics on predicting the congestion control selections. So again, we see that network type provides the most dominant predicting power for CCS. Therefore, we conclude that we can reduce the CCS to a learning task that infers network types from TCP statistics. So with that, we still have issues learning a generalized model that can be deployed across all the nodes over CDN network, mainly because of the hidden states in the network. So let me give you a concrete example to explain the problem. So for example, if we want to use congestion window as a feature X to predict the network types, imagine that we have two nodes, node 1 with a higher link capacity and node 2 with a low link capacity. Due to the high link capacity on node 1, we will obtain a high congestion window on node 1. And on the other side, since we have a low capacity on the link, we will have a low congestion window on the server side. So this causes some problems. So when we collect the data on both of the CDN nodes, we will see an inconsistent association between network type and TCP metrics. For example, on the node 1, we will see that Wi-Fi it has an association with a high congestion window. And on the node 2, we see that Wi-Fi has an association with low congestion window. So this inconsistency in the mapping between network type and network metrics causes trouble in learning a unified model for both of the nodes. So due to the time limitation, I will just give the key intuition that's how we address these problems. So the key idea that we try to leverage is that through measurement study, we find that there's a one-to-one mapping between the /24 IP prefix and the internet path or hidden states. So in order to learn a representation that is invariant to the hidden states, we just need to learn a representation that can be invariant to the /24 IP prefix. And this can be achieved by using the generative adversarial network or the GAN-based framework. So this is a complete architecture of our model. For more details, please refer to our paper and check the details. And secondly, we have the challenge of model interpretability. So the basic idea is that when we have trained the deep learning model, in order to interpret the model behaviors, we will first apply knowledge distillation to convert the DNN model to a decision tree model. And combined with Shapley analysis, we can accurately identify the key features for those prediction errors. Moreover, if we want to understand deeper, we can follow the path on the decision tree model to understand the model behaviors. To give you a real example, we have identified a low accuracy issue for the smaller ISP in our CDN network. So basically, by applying the method, we have found that the low accuracy issue is due to the over-reliance of our model on one type of TCP matrix in the early stage of our model deployment. So by pushing our model to use a wider range of features, we have successfully boosted accuracy for this small ISP. So finally, for model inference overhead, we have designed a pipeline to reduce the inference overhead based on two key observations. Firstly, CCS stays the same for hours, which means the congestion control choice is relatively stable over time. So, which means that we can save the inference results and reuse it for the future. This allows us to save the CPU on the CDN node. And the second one says CCS stays the same under /24 prefix. This means that we can not only save CPUs by save the inference results, we can also aggregate them under the same /24 prefix to save memory. So, so this is a full pipeline of our design. Basically, in the offline stage, we just collect all the TCP logs and feed them into the deep learning model. And once we get the prediction, we will perform some sort of aggregation and inject the results into the cache memory. And in the online phase, whenever a new TCP request comes, we can do a search in the cache memory, and whenever we have a cache hit, we can set the CCS immediately. Otherwise, we will fall back to the default configurations. And by doing that, we have achieved a processing delay reduction of 64 times and maximal query per second improvement of 2.4 times. So now we come to the evaluation. So we have deployed AliCCS over 400 nodes across almost all provinces in China and Southeast Asia. And we compare AliCCS with the baseline where we use cubic statically. So we have achieved an average rebuffer rate of 4.9. So just to give you some context about the number, even 2 or 3% of rebuffer rate reduction can ensure customer retention. So this 4.9% reduction is really significant. And also in this plot, we show that after applying AliCCS, we immediately see a rebuffer rate drop in the network. So also for the retransmission rates, we have achieved a more significant improvement in the retransmission. So we have, on average, achieved a 62% of retransmission rate reduction. and up to 174% of retransmission rate reduction. So to compare with the state-of-art solutions, we have chosen PASIAS representing the online learning paradigm and DISCO for a tree-based machine learning model. And also the more recent one, Configurator, which is a combination of both tree-based learning model and online learning paradigm. And we also include Oracle, which gives us the theoretical upper bound. So here we show the results of both retransmission rate and rebuffer rate at different percentile positions. First, we can see that the results of all approaches are very similar in low percentile positions. Actually, this is reasonable because at low percentile positions, we are in with low rebuffer rate and retransmission, which means we are in good network conditions, and all CCs will perform equally well. So it's expected that no CCS will make any difference. And when we compare DISCO and Configurator, the two machine learning-based paradigm approach, the difference is highlighted in the right circle, and we can see that AliCCS outperforms existing methods by using the GAN-based model, which achieves performance guarantees in poor network conditions. So we also compare with PASIAS. The main advantage is basically we can avoid complex overhead in estimating reward of PASIAS. Just one last slide about the lessons we learned during the journey of developing AliCCS. The first one is that you have to maintain throughput stability for short video services. Actually, throughput stability is more important than average throughput for short video services. Because short video services, due to its low volume traffic, can be more sensitive to the fluctuation of net throughput bandwidth. And the second one, you need to deploy a fallback strategy, which means whenever you have a low confidence predictions from your machine learning model, it's better to degrade to the default configuration rather than trust the model's predictions. This will give you a more reliable solution. And thirdly, we have observed that CCS has shown enhanced performance in IPv6 networks. And after some study, we have understand that the advantages of IPv6 network is basically due to their stable mapping between IP prefix and the subnets, which helps to improve the prediction which help to improve the history-based predictions, which are required by CCS solutions. And that's it. With that, I'm ready to accept your questions.